Hello again, it's Tom in the shop. I just wanted to share a short video about the thought process as I head into my next project. Up until now, all the gears I've made on my hobbing machine look pretty much like this. They're spur gears, and frankly, they've all been 16 DP, 14.5 degree, because that's what I got started making way back when. And that's what all the change gears for my hobbing machine are, that same pitch. Now I want to start making helical gears, I think, because when I think about kind of the next steps in terms of machines that I might like to make, some of those will certainly have a helical gear system in them. And frankly, you know, if I ever decided to build say a go-kart transmission or something like that, I would try to use helical gears for that, just because. So what I want to be able to make gears that look like this. And this just happens to be an M1. This is a cheap gear that I found on Amazon for about $9. It's 40 teeth, I believe. It's a module 1 gear with a 45-degree helix angle. So relatively common setup. And what I wanted to talk about a little bit was the different ways you can hob this kind of gear. There's two main approaches that people talk about. And again, I credit my YouTube friend at LSCAD for explaining this to me. I think I'm going to try a little bit of a practical demonstration here to try to illustrate it a little bit better than I have in the past. This is an M1 by 20 degree pressure angle hob mounted on a 22 millimeter arbor. And I've attached my gear to just a piece of aluminum that I'm going to hold by hand to illustrate the two different types of helical gear hobbing. One is called the Grant process, which I believe was developed in the US, and the other is called the Pfauter process, P-F-A-U-T-E-R, which was developed in Germany, I believe, Germany or Switzerland. And these two methods are significantly different. The Grant method is the one that you see most often on hobbyist machining sites. And the Grant method looks like this. Remember, we're always cutting in the direction of the hob. So for purposes of this demonstration, this hob axis is going to remain constant, and we're going to vary the work holding and the table angle in these two different examples. So in the Grant method, I've got the gear meshed, the M1 gear meshed with the M1 hob. In the Grant method example, the table feed is in this direction. So the work holding has been reoriented at 45 degrees to match the cutting angle of the hob. And the table is being advanced like that. And as you can see in this setup, it doesn't require any correction to the work holding angle. So as you're hobbing, this thing is spinning synchronized with the tooth passage of the hob, but you're feeding in this direction. So the relative angle of the work stays the same and stays in sync through that whole process. Now the Pfauter method, you're feeding this way. So the feed is along the axis of the gear. Now watch what happens to the gear as I move it through the complete cutting trajectory. You can see that it has to rotate through along the helix angle. And basically what that means is that for the Pfauter method, when I'm feeding this way, I have to be rotating the work in order to keep the cut aligned with the helix angle that I'm trying to achieve. Now, I think everyone understands the right-hand rule, but in case you don't, if you imagine that this gear is a screw and it's engaged in a thread that matches the helix angle, and if you rotate that 360 degrees, so in other words, one revolution, the lead is the distance that gear would travel forward. And it's a function of the circumference of the pitch diameter, the pitch circle, and the lead angle itself. So the actual formula is pi times the pitch diameter of the gear divided by the tangent of the helix angle. So in this case, the pitch for this gear is about 4.5 inches. So if I rotate that 4.5 inches, or if I rotate it 360 degrees, it would have to move 4.5 inches forward to stay engaged in that imaginary thread. And a right-hand gear, you rotate in the direction of the fingers of your right hand, the gear advances in the direction of your thumb. If this were a left-hand gear, the same would be true in the other hand. I don't have a left-hand gear yet, but try to imagine this one's going the other way. I don't know, this is probably Rev 6 or 8 or whatever. Not even really a complete sketch yet, but this is my initial design thoughts for what I'm trying to do. This is a cross-section, a vertical cross-section along the length of the spindle. And it's pretty much to scale, so it's going to be something like 18 inches long and so high and so wide. Basically, the objectives here, I want to change the final ratio from 90:1 to 40:1. I want to have a flexible kind of change gear system to allow me to alter the feed rate for different materials and different tooth sizes and so on. I want to be able to do the lead compensation to let me do the Pfauter method for making helical gears. And I want to change the arrangement for the final work holding end of the system to allow me to mount a chuck or a faceplate or a center or a collet chuck or whatever I want. So if I start at that end, I'm doing an L00 standard lathe nose taper with a key and all that stuff on the front end of the spindle. That's going to be interesting. So the bearings, the main support system in here is all going to be angular contact ball bearings. These ones here, the ones that really define the precision of the axis, are going to be ABEX 7 angular contact super precision ball bearings. That's a whole different game for me, and these bearings are, oh my God, so much better than the usual cheap crap that I've been using. So it's going to take some extra fancy machining here. I'm going to have to do some spindle or some tool post grinding, and so that'll be a lot of fun. So let's start with the input. The input comes in through this system here. This is a worm and gear setup that I made about a year ago. thinking that I was going to apply it in this project. So I've got it handy. But that's a 40-to-1 gear. It's way overkill for this project, but what else is new? So the input comes in through this, gets fed back to the change gear setup, which I'm not showing here, but there'll be change gears that drive the table feed screw. It also gets fed this way into a differential, which allows me to feed in the lead correction motion and change the ultimate angular relationship of the work holding axis, which is this bit here. So this is a conventional differential. I feed the lead correction in on the drum side this time. So there's another worm and gear set up here. That's going to be 120-to-1. And this shaft right here is turning at the same speed as the feed screw. So it goes through a pair of bevel gears there and then a set of change gears that provide the correct ratio for the lead that I'm trying to provide. So I think that this is going to be an interesting project. Obviously, it's complex. There's a lot of machining here. Some stuff that's new to me, like fitting those fancy ball bearings. So there'll be a lot of learning involved in this, which is the name of the game as far as I'm concerned. Well, you all know what this means. It's time for a little bit of math. But in this case, it should be pretty quick and easy because we're going to talk about lead compensation. If you look at the helical gear, remember with the Pfauter method, we want to feed this way along the axis. And imagine this pointer is the cutting edge of the hob. So the hob is spinning in a direction that's consistent with the helix angle. So we want to be cutting this way, but we want to be feeding this way. So what that means is as we feed through the hob, the cutting zone of the hob, we need to make this kind of change, this kind of correction to the motion of the workpiece. Now remember, this thing's going around in a way that's synchronized with the rotation of the hob. We have to do that so that we get the right number of teeth and the right profile. But on top of that motion, we have to add this motion, which is the correction for the lead of the gear that allows us to cut an accurate helical tooth profile. So the lead is defined like this. It's pi times the pitch diameter divided by the tangent of alpha, which is the helix angle. Pi times the pitch diameter is the circumference of the pitch circle, and the tangent of alpha is just exactly what it says. Let's draw a little diagram. This is the edge view of the gear. Here are the teeth, sort of, and that right there is the helix angle alpha. And the lead can be anything. If you've got a very small helix angle and a very small gear, it can be a few inches, or it can be a substantial number, like 100 inches. If it's a gear like this, I think I calculated this out, it's like 4.6 inches is the lead for this particular gear. The diameter and the helix angle yield that result. So we need to add, we've got this thing rotating like this under the influence of the index train. We need to add this motion to it So when we're talking about adding motions, we're talking about a differential. So we're going to add another differential to this machine. Let's draw the same diagram that we made before. A and B are the wheels on the car, and C is the drive shaft. And this works exactly the same as the last differential we talked about. We added a gear train between B and C on the index train so that we could get the correct index ratio for a variety of different gears. In this case, what we're going to do is put a gear train between C and the feed screw on the mill, on the horizontal axis of the mill. And because what we're trying to do is compensate for the feed position of the workpiece. And I'm just going to represent that with a set of change gears, A over B times C over D. This is kind of a generic expression for the ratio, and there may be things that we'll do to embed some parts of that ratio in the machine. But if we go back to our relationships for differentials, the defining relationship is A plus B over 2 equals C. It just averages the inputs. In this case, B is going to be our input, A is going to be our output, and we're going to adjust the motion using the drum, C. And when we solve for A, we get this expression, A equals 2C minus B. Now, let's imagine that there is no motion going in on the index, from the index train. Let's imagine B is set in concrete and we're not going to move it. How much, what sort of input on C would it take to produce a full revolution of A? And we'll just do that. We'll set B equals 0. We'll set A equals 1 revolution. So C equals 1/2. And we kind of knew that. Rotating the drum a half of a revolution produces a full revolution of the output A. So that's what we want to be able to do. We want part of our calculation to be what produces a full revolution of A. So if we look at our gear train, we've kind of got the inputs divided by the outputs, and the output is C, that's 1/2. The inputs are the lead. So we think about what we're trying to do. We need to produce a half a revolution of the drum as the table moves through the entire lead distance. So imagine yourself, say the lead for a gear is 10, you've got to turn that crank enough to produce a 10-inch travel in the work axis. And at the same time, we're trying to produce a half a revolution in the drum of the differential. So if you look at the input to that, it's the lead times the number of revolutions per inch of the mill, and in most cases it's 5, because most common machines are 200 thousandths per rev, divided by C. So it's L plus 5 divided by 1/2, which is the same as L times 5 times 2. So the overall ratio, if we take our example L equals 10, then it's the same as 50 times 2, which equals 100 to 1. And that's the gear ratio, the overall gear ratio that would be required to connect the lead screw to C in order to produce the correct lead correction for the output A, which is actually the work spindle. Now that's a big number, and one of the reasons we can deal with that is because this gear right here, this is another worm gear. This one's going to be a Mod 1 worm gear that's set up with 120 turns per rev, 120 to 1. So, in effect, I can divide that 100 to 1 by 120 to 1, and the actual ratio for my change gear set in this specific example is 0.833, lots of threes, to 1. And that's a very doable thing. And there's online tools. There's a method that you can use. It's in Machinery's Handbook for extracting the gear numbers for A, B, C, and D. The few examples I've looked at give me a bunch of very unique numbers. But in general, when you do this, when you kind of synthesize a change gear train, you can get within 5 to 7 decimal places accuracy. And for most gears, when you're only making a relatively narrow gear that doesn't use the entire lead, it's an acceptable error. So that's the essence of lead compensation math. It's really, when you think about it in terms of what you're trying to do, moving the table through the lead that produces a certain motion in the workpiece relative to the input, it's actually pretty simple.